I don't think that was what I was supposed to. I'm really not sure what just happened. But, I have no idea if this is working. But, let's see. Well, who knows what's happening. Anyway, so what I want to do is talk to you guys about the amino acid, and the most important thing is to talk about the backbone of the amino acid. Just like we have carbon backbones in triglycerides, and we have carbon backbones associated with the straight chain, and actually even the ring structure of simple sugars like glucose and fructose. We also have a backbone for amino acids. The backbone is a little different though. It's not just carbons. We do have a carbon that's right in the middle. So let's see. Let me use black just to be consistent here with what we have in our class. So we have a carbon in the middle, and then we have another carbon over here. However, on this side, we don't have a carbon. We have a nitrogen. Okay. And then we have hydrogens, and I'll do hydrogens in gray. And we're going to have a hydrogen up here, a hydrogen here, and a hydrogen here. What's interesting about this, though, is that because we have this filled up like this, it's actually going to be a positively charged end on this side. And then we have another hydrogen here. But over on this other side, we have a double bonded oxygen and a single bonded oxygen with a negative sign. Okay, so in this case, it's not truly ionic because you have a positive and a negative side, which cancels itself out. But certainly you have sort of a polarized situation, just like we saw with water being polarized. And then very importantly, we have something called the R group. So the R group is not part of the backbone. Okay, the R group is what gives the amino acid its identity as its particular form of amino acid. And if you flip to the last page in your Biomolecules 3 handout that I gave to you, posted on Blackboard or posted on Dropbox, you'll see a whole bunch of amino acids. In fact, there are 20 of these amino acids, and all 20 have different R groups, which is what defines that particular amino acid. So what's important to look at here, there are a couple things that are kind of cool and should be familiar to you. We have what I'm going to circle up in yellow here, something that's a familiar functional group. That's the amino group. Over here, I have a carboxyl group. Now, it doesn't look like a traditional carboxyl because it's missing its hydrogen, but you'll see in the next slide how it actually does become a carboxyl. Okay? So let me just label this so that you'll label this in your notes. And by the way, oops, forgot to tell you, this should go in that second slot on the front page of the handout I gave you guys. So the part 3 thing. And then, so that's the amino group, and this is the carboxyl group. 2 functional groups with which you should be familiar. And this is often referred to also as the acid side, which makes sense. That's why it's called an amino acid, each one of these things. Okay, now this particular form is called the Nonzwitterion form of an amino acid, FORM, that says right there. That's different from what I'm about to show you. So, can I get another slide? Okay, how do I get a new slide? I'm going to have to pause this for a moment. I really hope I didn't lose something, but anyway, the counter restarted at 0. Okay, so now that was the Nonzwitterion form. What I'm going to show next is the Nonzwitterion form. So in the Nonzwitterion form, we have the carbons, just like we saw before, and they're bonded to the red nitrogen over here, and we have the hydrogens surrounding them. So we have hydrogen here, we have a hydrogen here. However, in the Nonzwitterion form, we're only going to have 2 hydrogens, and therefore it's not charged. Okay? And we have a hydrogen over here, and we also have, over on this side, we have the double bonded oxygen, single bonded oxygen, and then very importantly, in order to make sure we still have the same fellas going on here, we get that H all the way back. So that H that was once hanging out over here now just transfers itself over to there. So you still have the same number of atoms involved. It's just the placement of the atoms is different. And the placement of those atoms, what the... I really have no idea what happened, but for some reason it totally deleted that whole thing. So I just had to redraw it again. But this is the, like I said before, this is the non-Zwitterion form of an amino acid, and I also did not include in this one the all-important R group. So you'd still have the R group sitting there that would determine the actual amino acid's nature, and then I forgot this hydrogen that was up there as well. So again, this looks exactly the same, except we just moved the H that was associated with the amino group over to the place where we have the carboxyl group. And now you can see it looks more like the traditional carboxyl group that you guys built up way long time ago. Okay? Okay. Now in the third section, this is the last little block of area for you on the first page of molecules of, or biomolecules 3. And what I want to do here is to show you how you bind together two adjoining amino acids. Now I'm just going to use black here just to make it a little bit faster for me to write these things out here. And I'm actually going to use the Nonzwitterion form. So I'm going to have the positive side of the amino group over here, and the carbon, and then the other carbon double bonded to oxygen over here, single bonded to an oxygen here, and then we have some sort of R group. And let's say, just for argument's sake, let's just say that this is the R group that would make this one be called glycine. Okay? And we have next to it, we want to add, oh, you know, I should be careful about that. I don't want to, is there no way of going backwards here? Man, I really want to erase that plus sign. Well, I won't. I'll just leave it in there. All right. So, and then I have adjacent to this, I have another amino acid with its own plus sign there. That plus sign in the middle there is in addition. I'm going to put them together in just a moment. And this also is associated with the nitrogen, its other two hydrogens. We have a couple of carbons here. And we have a different R group here. So since this is a different R group, I'll make it a purple R, just so we know that there are two different ones. And we'll just call this one, I don't know, isoleucine, let's say. They're funny names for amino acids. Okay, so ultimately I have these two independent amino acids and I want to bind them together. And the beauty of it is that it's pretty easy to do this because you've done it before. We're going to do a dehydration synthesis reaction. So we're going to take this oxygen right here and these two hydrogens right here, and we're going to combine those two to ultimately make your favorite pal, water. Now if you do that, if you lose those two things, then you're going to end up with a single hydrogen by itself associated with that N, and you're going to have a double bonded oxygen all by itself associated with that carbon. So this will look like, when we're all said and done, the next page. So let me just give us the next slide to take a look at what this looks like. Okay, so you shouldn't be too surprised that this is what it looks like when it's all combined. And notice that you could easily continue to do this. You could take another amino acid and you could add it to either end. You could put another amino acid over here, or you could stick another amino acid over here. So as long as you have that backbone, it's the backbone that holds together successive amino acids in a long chain of amino acids that ultimately make up your protein. Now, this bond right here, it has a very specific name. It's a covalent bond that exists between the carbon and the nitrogen, but we have a name for it that is going to be important. It's called a peptide bond. And in fact, we call a chain of amino acids a polypeptide. Poly meaning many, peptide meaning the bonds, so you have many bonds making up this polypeptide chain that will exist. Okay? Don't forget, water is produced whenever you bind together 2 amino acids. You produce 1 water. So it's always n minus 1 for the number of waters that you're going to be producing in this process. All right, there's only one more thing that we need to cover, and I'm going to start it on the next slide.